sigma of x greater rho. The kernel function or density function generated by the sigmoidal function sigma, we have this definition. It is easy to verify that the density function is non-negative and even. It is non-decreasing on the interval minus infinity to 0 and not increasing on 0 infinity. For the kernel, we have the following three properties are verified. This identity, the property of unit, the function p of 1 is between 0 and 1, and the kernel function is infinitely less than this function when x goes to plus and minus infinity. Here, I will give some examples of sigmoidal activation functions. Some of them are used in our study. Logistic function is one of the famous sigmoidal activation functions. Tangent sigmoidal function. I presented before an example for this function. Ramp function, starting from the B-spline of order n, this function. We can construct using this integral transform activation function. Another important activation function that we use in our study is ReLU activation function, which is defined as the positive part of x. We have a connection between the activation function derived from the B-spline and this ReLU activation function. We have this connection. The activation function derived from B-spline with of order n equal 1. We have this representation in terms of ReLU function. The density function in terms of kernel function, in terms of ReLU activation function, is given in this relation. We wanted to implement an algorithm based on neural network operators. So in the following, I will give the definition of multivariate neural network operators. We consider this Cartesian product. 0 is the space of all continuous functions on certain set, defined on certain set. Consider the multidimensional kernel defined as the tensorial product of the kernel in the univariate case, and kernel verified the following three properties. It's infinity less than this function, where this is the Euclidean norm. The kernel function belongs to the space. The following is identity is verified also unique, and for every gamma positive, converges uniformly to 0 in respect to x. And here we have the of the neural network operators, so the multivariate version or neural operators, where C is a kernel defined in the previous slide. And F is a bounded function. Pointwise convergence, uniform convergence for the, and for the, we have a uniform convergence of these operators. This result was published by Costa and Ziegler. Want to compare the algorithm more on the operator.
Non abbiamo visto nessuno.
Non avete sentito la precedente?
No, è saltata la connessione.
No, è saltata, ci dispiace, ma non stava parlando e non ce ne eravamo accorti.
Sì, certo, nessun problema.
Allora, vuole condividere le slide? Per favore, e poi la presento.
No, sta bene.
Come?
Sta bene.
Ah, adesso ok. Ah, sta bene. Era convinto che ci fosse.
Vede le slide?
Lei vede le slide?
Sì, ora sì.
E le posso dire? No, ma se va via la linea intanto non ci sei. Ok, adesso controlliamo magari intanto.
Ok, grazie. Non vedo le slide di nuovo.
Come?
Ah, e allora un problema. Adesso? No, andate a vedere la condivisione.
Aspetta, era questo, aspetta.
No, è quando facciamo le controlelle. Così le vede.
Così le vede?
Sì, ora sì.
Le vede?
Sì.
Adesso ti dica, dici se le vedi, aspetta, Vediamo tutti del tuo, va bene? Le vedi così?
No.
Allora facciamo una cosa, un attimo.
Però invece di fare il controllo e farlo da
No,
sotto.
facciamo condivisione dello schermo intero.
Forse. Stanno tutti i computer con linguaggio tu. Permetti di vedere, no?
Ok, adesso invece?
Sì, ora sì.
Oh, perfetto. E questo...
No, io lascio il prossimo.
Perché serve per la connessione. Okay, so next speaker is Professor Ivan Devate from the University of Tijuana over the organization of this session, and the title is Digital Reconstruction of Ancient Paper. Thank you.
Good morning. I'm going to present a talk about anti-planning, in particular in the second half of the 19th century, in the formal Papa state, there were different place cards that varies between the Romagna one to the Viterbese passing to Perugia. This is the Romagnole desk used by Buralisa company from Bali. This one is the one that I'm going to study in this talk. And this other one is the Viterbese one. All of these are approached by Murali from Bali. Another type of the desk that we are going to examine is this one. This is of Murali, and this is from Ambrosio of Padua. In the area of Perugia was produced. This is still a new kind of this type that they are going to examine is still Muraggio Valley. This kind of death was used by Mariani. in the city of Perugia, of the 19th century, the producer of playing cards was mainly two, Bartolini and Silvestrini, and both was in the area of our department. And as regards Bartolini produces this ace of coin, this is the same of the one that used by Murari. So we are going to refer to this card as Perugine one. Because this type of card was of the 12th century, and this was the perfect yes, this kind of type of we that is early space. To obtain luminance of this space, we can use this transform, while to add the chromium, we can use this other transform where alpha and are the coordinating this chromium space. And if we consider the star, this is the luminous component. This one is the chromium component. This one is the component. This is the alpha component. This one is the beta component. Then first we try to increase the constant and change the curve of the car. So here is this image. It is the effective image. If we fix some of this component, then we apply this transform where C are the contrast points. And then we obtain the luminance and the chromium. We start now with the luminance, and we go to the blur and the noise this component. The solution is given by the numerator of the following energy function. The energy function is by two terms. This is we take this image, the blood image. This result must be equal to our method, and this is the movement. In this movement system, we have this stabilizer, and that is all. This form, and also this form, and this term is the this second derivative in the C of the luminance. This is this second derivative in the senior quality associated with of the luminance. So if we use this kind of term, the retrospection will be edge preserving, and moreover, we are going to with a closed parallel line. S is the threshold to introduce a discontinuity in our expansion. Get a closed discontinuity. This energy is not complex, so to find the meaning of this energy, we use a new problem. Find you want to declare the chromiums we function. These are two data consistency terms. While this is the smoothest term, this is the smoothest parameter, and this is the first derivative in the alpha component. This is the first order derivative in the beta component. Why this is the discontinuity that we have already estimating during the computation of the alpha component. So all this term is complex. And then to minimize this function, we can use a subtype algorithm. So for this phase, if we consider this as our data, these are the results. You can see that we change the color and the blending with the oscillator. Now there is a phase for the point we one. If there is some little gaps in the black line, we cover it by using implement this space in the then the result of this phase is this one, and now we want to implement the homogeneity in the area in the between the black. So we define this kind of filter for the first order, in which the pixels are there are no black pixels in both of these two sides. Then we minimize the energy function in just in the sorry. One moment, I come back to just in the C1 star. In survey, just we make the smoothness in the area between the borders. In this case, the function is minimize it by using a solar. This is the result. This is our data. This is our result. Notice that here we draw the black rectangle using the unseen. Then we want to estimate the external control. So we want to regulate like it. So we proceed in this way. In a row, if there are just few in a row on the form, the way just to white pixel between black pixel, we color the pixel by one. No, it's the reverse. In this case, if there are white pixels between black pixels, like we call white pixels are colored by black, the black pixels are colored by white. And then if we have two black pixels that are followed by colored pixels, we can increase the number of black pixels until we reach a value of given pressure. Then, given this result, we want to construct an image that has just three values, white, black, or colored background. So we consider that row, the column of our image, and all the other along this direction. This one, this one, this one, this one, this one, and this one. Then, if there is a black pixel between some color pixels, we consider this black pixel as colored one. Then this is our data, and the result applied that. So external border of the image. Now we want to regularize this external border. To regularize the external border, we consider this is our data. This is a generic trigonometric image, and then we define this function. This function is equal to 0 in a pixel if y is different to y. And then, given a trick of the first order, we consider this other function, and this function is equal to 0 if there is not a step in the trick. Then, given the set, which is the set of the color pixels in the y image, we define this function that is equal to 0 if we have a white pixel between the border, and this is the value of the distance between this pixel and the set of the color pixel, and a pixel value there. So we minimize energy function. This is a sort of closest term. This one is these two are two smoothest terms. This is we don't want that we have too many in our image this term. And by this term, we want that the thickness of the border is almost constant. To this function is a discrete function, it's not complex. It's difficult to find a complex approximation in this function, so we use the simulated analytic technique. Then the result is this one, this is our data, and we obtain this kind of result. For the last step, given an image with the border y0, now we have a regularized border y1. So we want to find the image x6 that has this new border. So let we set the set of the new white pixel. This set is the set of the new black pixel, and this set is the set of the new color pixel. Then this set is the set of the previous color pixel. So if a pixel belongs to y1, we color the pixel by 1. If a pixel belongs to the set v1, we color the pixel by black. If the pixel is in the intersection of n1 and n0, we set the pixel to be the same as before. Now we consider this set of pixels as sigma sharp. It's the set of the new color pixel where see there is no a border. So we estimate the solution in this area, minimizing this function. Psi is the function that I find before, so the result is and about parallel closer parallel. And so we have to use a GNC technique to find the result of the system. So the final result, this is what the starting point, and this is our final result. The have to determine a data collection model in some way to be able to numerical estimate the goodness of our result. Then, as we said before, we have to prepare a phase for process. We want to construct different historical important data, as for example, this.
Any question?
How good is this minimization function for the also a denoising part.
Here components the derivative in the but we want to have some fixed image. We don't have any border close by, and this is the case that we have a border close by, so we elevate this post in
This general method that you use can be useful also to reconstruct writing of ancient texts, or is it specific for
test, we adjust this part. So I will do
the border?
on the border. The image in the paint cards. Yeah, very homogeneous. Quite often we don't have. So if we recognize all the comics, this one, because if you see here, this is a little bit, this is not very well smoothed, just because when they print the cards, the sound move, and you have to smooth a little bit. This is just for the The first one was general, completely general.
Another comment, do you, I don't think for such a problem you have a ground truth, in the sense that you have this old card and you want to reconstruct this old card in order to denoise this card or something like that. But you do not have the original card.
No, I don't have the original card, I don't know.
So you cannot have a ground truth in order to compare if the result is good or not.
No, yes, yes.
You can only say, okay, visually my cards now are restored,
Yes.
and so on.
The goal is for the moment to have a good restoration to give to some company as Damnego to print a new one because this the print the stuff is not good since the 1920
You only have a line. You have an old sense of this card.
yes, just a few just I have the scanner of the few of them because the system but
There is somebody that has
I am in the function of a transfer collector. I know where it started, and he gave me the scan, the standardization. Yeah.
Thank you very much. Elisa, vuoi condividere le slide?
Sì, certo. Ok.
Sì, certo. Ok.
Come si mangia? C'è adesso del vaso.
Vedete le slide, giusto?
Ok, so next week,
Giusto?
sì,
Sì, le vediamo.
forse è meglio metti un attimo.
Come? Tutto a posto?
Vabbè. Okay, so next speaker is Professor Lisa Cabru. Sì, senti?
Un po' a tratti, però vi sento un po' in ritardo, diciamo.
Ti senti?
Sì, a tratti.
Sì.
Ok, sì. Voi sentite me?
Ti senti?
Sì. Voi sentite me? No. Mi sentite?
Ah, qui. Ti senti?
Sì, voi non sentite
Sì.
me?
Senti? Sì, ti senti?
Sì, io vi sento.
Anche noi.
Ok, perfetto. Ok.
Quindi che non preoccuparti, che noi la sentiamo bene. Okay, so next speaker is Professor Lisa Cabru from the University of Cagliari, and the title is The Tool for the Construction of Synthetic Petroglyphs. Okay?
Okay.
Elisa, you can go.
Okay, thank you so much, and good morning to everyone. And today I'm going to talk about a MATLAB tool for the construction of synthetic petroglyphs. This is a joint work with Professor Alessandro Buccini. And before discussing the tool, before talking about the tool, I want to explain why we create this tool. We are currently working on a project that concerns the documentation of petroglyphs of the Domus de Jana sites, which are funerary hypogea, founded in Sardinia, dated 4 millennium before Christ. And a part of these rituals was to engrave, to carve the walls with different shapes, in mostly cases geometric shapes, and several automatic approaches have been proposed to extract these glyphs from the surfaces, but they only have been tested on real data. So we create a tool for constructing synthetic but realistic petroglyphs to validate segmentation and algorithm methods, and to create data set for testing machine learning algorithms. So the tool is very simple, so provides a graphic user interface that, by selecting some parameters, allow to create a desired curved surfaces. So by choose the position of the glyphs, the shape and depth of incision, one can create a lot of data, a lot of curved surfaces. And in this image, you can see the graphic user interface. So in the top, the user can select different parameters, and we will discuss about that in a few minutes. And then in the bottom, the user can see the surface that the result of the method. And this surface is the results obtained using the default parameters. And in here, in this side, you can find the MATLAB application. So the package is composed by 5 files. The first one is the MATLAB application. The second one contains 2 backgrounds on which we can carve the petroglyphs, and the other files contains a function that allows to create the glyphs. And we will discuss about all of them in few minutes. So the user start by choosing a background, and then the glyph that they want to carve into this background. We provide the user 2 different backgrounds obtained from rock walls of domus sites using the photometric stereo technique. I will just describe the main steps of this technique, but you can find all the details in the paper that in the preceding paper. And so the photometric stereo is a computer vision technique that provides a 3-dimensional reconstruction of an object starting from a set of images. So the configuration consists in a camera fixed in front of the object, and the lights are placed in different positions around the object, such that each image of the dataset is obtained from a different light direction. And these light positions are theoretically known. And also, we assume that the reflectant of the object is Lambertian, so satisfy the Lambert's law. So the intensity observed from the observed intensity is proportional to the cosine between the normal vector and the light direction. And rho is a quantity called albedo that takes into account the partial absorption of the light from the surface. So by discretizing the problem and ordering the pixel lexicographically, the Lambert's law can be expressed in this matrix form. The known lighting configuration as a trivial solution, but the unknown lighting configuration is quite difficult, but the Hayakawa's techniques provide a method to estimate the normal vectors and the light direction from the data, and then by solving a Poisson problem, we obtain a discretization of the surface that provide the shape of the object. But since some of the assumptions cannot be met in real application, especially in the archaeological one, leading to inaccurate reconstruction, also the method can stop without obtaining any kind of solution. We individuate 2 numerical indicators that allow to extract from a large data set a subset of images which provide a good reconstruction and accurate reconstruction of the surface. All details about the photometric stereo technique and these 2 numerical indicators can be found in this paper. So using is everything okay? I hear something. No. Okay. So the user can choose between 2 backgrounds. The first one is obtained from considering a portion of Domus Tejanas, the Domus Tejanas of Coronjo Pimentel. We consider the top left portion, since here there are no glyphs. So using the photometric stereo, considering 13 pictures, the first indicator extract 9 pictures from which we obtain this reconstruction, which is a three-dimensional reconstruction. So this is a surface, not an image, okay? This is the first background. The second background is obtained from a wall at Siligo, and archaeologists are still debating if this wall belongs to a Domus de Janus or not. In this case, we consider 18 pictures, and the first indicator extract 17 pictures, and from these pictures we obtain this reconstruction, which is quite accurate, and this is also a surface, not an image. So the user can choose between one of these two backgrounds, and then you have to choose between different shapes. We provide the user two different shapes, a spiral and a jagged line. Since in Domus de Janus the glyphs are mostly composed by these two shapes, we consider only these two. But it's trivial to extend the tool with other kind of shapes. So I will define now how these two shapes are defined in our tool. The spiral is defined as the area between these two curves, and the segment joins the values of these curves in 0 and 2rp, where r is the number of rounds of the spiral, and ws and d are the width and the depth of the spiral. And in this case, it's trivial to show that S belongs to the square. The jagged line is defined like in the same way, so it's defined as the area between these two curves and the segment connecting these points, where mode J2 is equal to 1 if it's even, and if is 0 if it's even, and 1 if it's odd. And in this case, N is the number of peaks of the jagged line, WS and L are the width and the length of the jagged line. And also in this case, it's trivial to show that J belongs to this square. So the user can choose between you have to choose the background, the jagged line, and then how the glyphs are carved inside this in this background. So we assume that the background can be represented by this function, and we define the function that represents the carvings of the spiral and the jagged line as is and ij, where tau s and tau j represent the size of the spiral and the jagged line respect to the background. Delta s and delta j represent the depth of the incision, and xs, yns, xj, yj represent the horizontal and vertical shifts of the spiral and the jagged line, respectively. So by defining these two functions in this way, the edge of the carving will be extremely sharp. So to smooth them, we consider a Gaussian kernel K with standard deviation sigma, and we define a curved surface in this way. So the background and the two carving functions, where star denotes the convolution operator. So once the user choose one of them, choose the background and the spiral and jagged line parameters, can construct any kind of surface only by choosing different parameters. And I will show you this with two examples. The first one is this one. So this is a graphical user interface. The user can choose different parameters, and all the parameters are described in details in the paper. In this case, we consider the first background and both the spiral and the jagged line. And by fixing some parameters, they will come in this place, are positioned here. And so the user, by simply use the button create glyph, can see the bottom, the solution surface, not an image of surface. And the tool save the file .mat contain the surface as an axis. And so this is the first example. And the second one is different because we consider the second background here, and only the spiral. In this case, we consider sigma equal to 10. So the edge of the spiral here blurred. In this case, the algorithm, the algorithm struggle more than in. And with this tool, one can bicycle this parameter a lot of spaces, and with different shapes in different positions and also using the background. So it will be useful also for algorithms because we want to create a training data set which contain a lot of curved surfaces. And thank you so much for
Thanks very much for your talk. And question, Mark? This study was inspired by the fact that in Sardinia region you have this site and there is a connection between you or some professor and this, how it was inspired this study.
yeah, and encouraging the of the messages. This is my PhD project. So this connected with my PhD project. And we are also collaborating with people who are interested in this kind of.
Okay. If there are not any other questions, we thank again the speaker. Okay. Next speaker is Professor Wolfgang Erb from the University of Padua, and he will speak about split and merge segmentation of biomedical images using graph wedgelet decomposition. Thanks.
Adesso dovrebbe essere
metti l'intero schermo, se no poi non riesci a fare la connessione. L'ultima voce a destra. Fai controllare.
Thank you very much for your introduction. So I will talk about the split and merge segmentation scheme for images. So split and merge means we are first splitting the image in smaller parts, and then we try to use the smaller parts to do a segmentation of the image. And the main object why we are doing this first splitting scheme is to reduce the computational cost. So if we're trying to do a merging scheme on the entire image, this is typically computationally much more expensive if we first apply a split scheme. And yeah, I will describe how the split scheme works and split scheme works, and then how the merge works. Okay, so okay, this is how the split works. So it works in terms of when the image in terms of I don't know how the mouse comes in. Okay. But what I'm trying to do is to approximate a limit with piecewise constant elements, so with piecewise constant segments, and I'm trying to use a kind of deeper planes to separate this image. So this is now a piecewise constant approximation of a much more complex image. Can you maybe imagine what kind of image it is? Okay. So let's see how it works if I'm using more splits. So now I'm using 20 wedges to compose that image. Still not clear. 200 wedges. Okay, now that's clear. That's the bridge here in Istanbul. 2,000 wedges, 20,000 wedges, and here from the 20,000 wedges, yeah, to the original image, it's not a lot, but yeah, you can see that some details here are still missing. It's because I'm using an approximation of the image in 5,000 splits, and now at the end I can use these splits, still merge the image together, and at the end I get a segmentation of images, 18 in total domains. So how is the splitting, or what is the aim of this presentation? Is use splits, these adaptive wedge splits to get this decomposition of the image, and then to do a merging strategy to get to segmentation. For instance, for medical imaging, we're interested here in this glioma and the segmentation of this glioma, and we can do this three steps. So this is the original one, this wedge split, and once I have the split, I can then do segmentation in the second phase. So yeah, there's a lot in the literature about these splitting schemes, in particular for images. So there are images based on wavelets, there are adaptive triangulation, there are quadrants, tetralets, and also wedgelets. And the theory that I will skip on that I will rely on are the last two. So I will mainly use this continuous wedgelets and also these binary space partitionings. And I use that in combination with a graph structure. Yeah, so this adaptive splitting allows to decompose really the image then with a relatively small amount of subdomains. So you have these wedgelets. You can then decompose the image like that. For instance, this here is a quadric decomposition. You get then a decomposition like this, and all of them allow to represent then the image with a small amount of pieces. And once you have these pieces, it gets really easy then to do the merging part. So with a small amount of pieces, also the computational effort for the segmentation process is then quite small. And these are things that you can then also you can then also apply them to graphs. And why are graphs useful in this context? So in contrast to images, so you can always look at the graph also as so a graph is somehow a generalization of what you have there. And but the graph is more flexible. So if you have video, so if you have higher dimensional data, you can also use that, or you can in a very efficient way. Okay, yeah, graphs are generally defined like this. Vertices, Okay, so typically then the image is then just a bunch of pixels. So this function f that will represent in the two that we can represent this image in terms of our theta or a function on the set of images or the set of nodes. Okay, and as for images, I can do the same about that. Usually adaptive procedures, and what I did there about some kind of adaptive decomposition in terms of webs. So I take two nodes of my graph, and then I'm splitting the graph into parts based on the closeness to this vertex. So if I have a vertex which is closer to this one than to this one, then I will assign a node here to this node. And in this terms, I can define a base split. And once I have a split, I can split the image and with several other nodes and consecutive way. In total, I will then get the image. So if I have two nodes, then I can take every node which is closer to this one and link it then to this node. And if I have a node here, then it's closer to this one, and then link it to this node. And in general, I can then define a tree. So first when I have this split, then I can take here another node, and then another set. So this is the first node, this is the second node. Then I can split the image again. Also here in this case, if I get a second node inside this subdomain, I can split then the image or the graph then according then to the same procedure then again and again. And this allows me to generate this tree. And the only thing or the parameter of my trees are now the nodes, so the selection of my nodes, something that I can adaptively based on the image that I have at hand. So I can choose here these nodes in a good way, in such a way that I can that this tree is generated, and that in such a way that here also these splits are done in such a way that at the end I need a very small amount of splits to approximate my image. So and the corresponding characteristic functions based on the partitioning that I get is what I then refer to as wedgelets. And in total it looks like this. So I want from this nodes, then I get the first split. Here you see the same two nodes. Then I can continue, so I can insert here this node, then I get another split, then I can insert this node, then I get another split here, and I can continue this in another way. And then you see here after 32 splits, I get an approximation of the image of this. And I can code all the splitting in terms of these 32 nodes that I captured here. So this allows me to do this very efficiently and also with a very small amount of memory. I just need to store here the nodes that I'm using for that split. Of course, I need some computational effort and to calculate here the splits because I have to select here the nodes in some kind of 3D procedure. And I have to compare a lot of different splits. In such a way, I get also a very good, very sparse approximation of my image. So I can calculate this adaptively. So I'm using here the L2 error. So I selected here the domain where my L2 error is maximal. That is then the domain which is split in the next step. So I'm selecting a domain VQJ, which is based on a node QJ, and inside that domain, I'm selecting then a second node in such a way that if I split this domain, the corresponding split gives me an error functional here, an L2 error functional, which is as small as possible. I do give then the corresponding algorithm for the splitting. So I'm starting with one node, and then I'm selecting all the consecutive nodes in such a way that here these functionals are minimized. And at the end, I'm finishing with a set of nodes those nodes codify the tree and the corresponding values, which correspond to values for the piecewise constant approximation. And the decoding is then very easy. So if I have these values and the nodes, with the nodes, I can reconstruct the tree. And if I have the tree, I can assign then the values to the single domains of my tree. Okay, for the merging procedure, I have to do the same vice versa. So the starting point there is the wedgelet decomposition. So I have m domains and the corresponding mean values. And the merging strategy is then to have some kind of region model, which assigns me then, so if I have two regions R1 and R2, merging these two regions, then I need a corresponding function value. Here I just use the median for that, and I need also an order in which this merging is done, and for this I need some kind of similarity. So the two regions are similar if here this value is very small. So these function values here are very close by, then also this value will be very small, and then I will merge those regions where this value here is the smallest one. So I'm using this O here as a merging order. All right. So this is then the merging part. I'm defining here this merging order, this region where this value gets minimal, and then I'm merging them, and I'm assigning to the new merged region then this pixel value. Okay, the memory requirements are unfortunately quite low, so I need some amount of my memory to store the tree. But once I store the tree, I can use the same information and also to store the segmentation. So this gets a very, very efficient procedure also in terms of memory. And yeah, those are the things like this. So those here are now my splits, the approximations of this image in terms of piecewise constant elements. And once I have here these images, I can then do the merging procedure and go down to two domains. So I have then at the end just this white domain and the black domain, white domain, black domain, white domain, black domain. So here probably you won't see the details, but with a better approximation, of course, here at the end I end up also with a better state here and to represent better than the details of my image. So, and yeah, you can do the same application of the biomedical images. So the same way, I'm starting with the original image, then I have the splitting scheme based on this piecewise constant approximation. Once I have this, I can do the merging step, and I get this, and at the end I can select my view over here. I have a second application if you want, for instance, to extract the white matter, then you can do the same here. Original image, then you're doing this splitting scheme, then the merging scheme, and then at the end you can select then this white matter. But you see, so in this case I had also the ground truth at this position. So this is the ground truth, the threshold ground truth, and then the comparison to my to the segmentation with the algorithm. And here you see that there are still some errors inside. And this is, of course, the case here because here this approximation is also not perfect. So here this is a piecewise constant approximation. The details are at the end not exactly extracted. So here are always some error, and you see this error then also here inside the segmentation. But of course, you will get better if the segmentation here gets better. Segmentation, yeah, also the segmentation. But if here the splitting scheme is more advanced, if you're using more splits here, then you get a better approximation, and then at the end you can reduce this error. Okay, with this, I can finish here if you want to read more. So this is the paper that I submitted to conference proceedings, and this is the original paper where I derived some theoretical results regarding this wedgelet decomposition. Okay, thank you. For the method, are there any questions?
Where you have the apply this method to medical images of the brain. You said that you have a disposal of the ground truth. Have you calculated some similarity in between your linearization, your image linearized and the ground truth?
For this example, not for other examples, yes, for this year, I didn't use something like this. For me, I think the main so for me, the main index here is how many pixels are wrongly classified as a type. Yeah, they are correct. So it's in principle the difference between these two masks. So these are really 101 maps, and then here you can really measure how many pixels there are. But I don't remember exactly the. So I calculated it, but I don't remember exactly. But yeah, it depends also on the approximation. So I use different approximations. So the only thing that you can see, so if there is a better approximation, then here this white or this white pixels. Yes, in principle, so there's a lot that I could tell you about that. So in principle, what you can always use is apply the graph Laplacian to a signal x, and then in a product with x again. This gives you some kind of this gives you a positive graph Laplacian, it's a positive semi-definite. And for instance, for a constant signal, you would get 0 out of that because the constant signals are in the kernel of the graph Laplacian. And then you can go on, so you can think of the eigenvalues of the graph Laplacians as frequencies on the graph, and the corresponding eigenfunctions then as harmonic functions on the graph. And the larger those eigenvalues get, the more oscillating these signals then are. And so this graph Laplacian in this way gives you a measure on how oscillating, on how far away the graph signal is from the constant function. And in the sense that this graph Laplacian so in principle, the assumption there is, or the model assumption is that the larger the value gets, the more noise you have inside your. And what you can do is then you can decompose the signal in terms of this eigenbasis of the graph Laplacian, and you can take away maybe the ones which correspond to the higher eigenvalue. So in this case, this was an extension of what I did, because which I didn't show here because here I always use this as constant. But if you want to insert not just a piece as constant approximation, also something which gives maybe a better approximation of the image, you would also then consider linear or the eigenfunctions of the graph Laplacian as basis functions.
Of the fact that your model, whenever you are hit the first notes, I want to
Yeah. I was quite quick about that. And so the first node is choose according to this measure. So I'm looking at all the subdomains, and I'm considering this L2 norm of the arrow there, and I'm taking the subregion where the L2 error is the largest. So where the difference between the function and the function is largest possible. So where I don't have a good approximation of the function in terms of a constant function. And I'm choosing then this region. So this region is selected, and this region is then split. So maybe here in this example, so here in this case, if you do the split here, then here on this side, here the L2 arrow will be the largest on this upper side, and this this part is then split into two subdomains. So I'm choosing here this upper part, and then I'm doing here the split with this guy, and then in the next step here in this region, the L2 arrow is the largest, and then I'm doing here in this region then the next. So I have, and you can of course also use other arrow functions, but yeah, the L2 arrow
in this sense, it's possible that when you add the splitting phase, you can do nodes. What you're interested here is a kind of a hierarchical Bormer diagram of the image.
in some sense, yes. So it's some kind of a Bormer diagram on a discrete level. So it's yeah. So if you would use continuous splits, then yeah, you would end up with some kind of yeah of continuous of another adaptive Bormer diagram. And so in the literature, this continuous setting, if you want to look at, I think the most best thing here is the use of these binary space partitionings. The binary space partitionings, which were developed here by Vetterli and co-authors, they use hyperplanes that to split their domains. And yeah, so they use, yeah, here it gets more difficult from the coding because they are starting from the continuous setting, and then at some point they have to discretize it. And, yeah, the rough approach is more general and more simpler, but of course in R&D